Hello, myself Naveen Kumar Saini. In the course Electromagnetic Field Theory, code KEE 301. Today we lecture number 19 is there, and we are in the unit 5 waves and the application. So till now we have derived all the four Maxwell's equation in the time varying B field, E and B field. So these equations are because we have, when we go for the wave propagation, then before that we have to summarize all the Maxwell's equations, where first Maxwell equation in the differential form is del dot D is equal to rho v, and its integral form, that is d dot ds with the closed surface, is equal to rho v into dv with the volume, which is given by the Gauss law. Second is del dot b is equal to 0, where integral form of this one is b dot ds with the closed surface. So the significance of that one is the non-existence of isolated magnetic field. Third one is del cross E is equal to minus del B upon del T, and its integral form, that is E dot dl with a closed path, is equal to minus del upon del T B dot ds with the open surface. And this equation is derived by the from the Faraday's law. Next, last and the fourth equation of Maxwell equation, that is in the time varying field, is del cross H is equal to J plus del D upon del T, where we say that J is the conduction current density and del D upon del T is the convection or displacement current density. Then its integral form, this is H dot dl with a closed path, is equal to J plus del D upon del T dot ds with the open surface, and this is derived by the Ampere's circular law. So, in summarize, all these Maxwell's equations are responsible for the generation of the wave or the propagation of wave from one point to another point. So, all the derivations will be based on all these Maxwell's equation in the waves and its application. So, for that, when we want, if we say that the wave propagation, so this wave propagation will be into the medium, right? So, these mediums we have to discuss it here. So, what are different parameters for that, for those mediums? And before that, we know the definition of the waves. So, waves are transporting energy, okay, transporting energy or the information from one point to another point, and the wave propagation will be occur into the different mediums. So, first medium which we will discuss, that is a free space, and this free space will be defined as sigma is equal to 0, epsilon is equal to epsilon naught, and mu is equal to mu naught. So, this is the parameter which is defined for the free space, right. So, these three parameters, sigma, conductivity, permittivity, and the permeability. Second wave medium in which the wave propagation will takes place, that is a condition for that is sigma, that is sigma is equal to 0, epsilon is equal to epsilon naught into epsilon r. So, this is relative permeability. Then mu is equal to mu r into mu naught, and for that the condition for this one will be sigma is very much less than omega epsilon. Third one is the lossy dielectric. In the lossy dielectric, the sigma is not is equal to 0. This is a generalized case, and epsilon is equal to epsilon naught epsilon r, and mu is equal to mu naught mu r. So, this is a lossy dielectric case, which is not the perfect sorry, perfect dielectric, not the perfect conductor. Then fourth one is the good conductors. So, for that the conductivity will be very high, where sigma is equal to sigma tends to infinite for that, and epsilon will be epsilon naught and mu will be mu naught mu r. So, this is the case where we have the magnetic effect into it, right. And the condition for this good conductor is sigma is very much greater than omega epsilon. So, this ratio we will discuss about this is a loss tangent. Okay, we will discuss about this content. And so in our syllabus, as per syllabus, all these 3 4 cases we will discuss about that, right. And one more issue we will discuss about, that is the perfect dielectric, right. So, for those as we are very much aware about the different Maxwell's equation which we had derived already in the previous lectures, and the case which we will handle here, that is a free space where rho v and j will be 0. So, for the free space, sigma del cross h will be equal to epsilon naught del E upon del t, and del cross E will be equal to minus mu naught del h upon del t, and del dot E will be 0, because this is a case of the free space where there is no charge are present. So, in short we can say this one is del dot D is equal to rho v. This was the Maxwell equation, and rho v is equal to 0, right. So, rho v is 0, and in place of D we can put the epsilon naught E. So, it will be del dot epsilon naught E is equal to 0. So, in from this equation we can get the del dot E is equal to 0. Then we have del dot H is equal to 0. So, how we had derived this equation? We had derived this equation when we have the del dot B is equal to 0. So, in this case B will be equal to mu into H is equal to 0. So, mu cannot be 0. So, in this case we can write the del dot H is equal to 0. So, the first equation states that the E is changing with the time at some point, then H has the curl of that particular point. Okay. So, in short we can say the H varies especially in direction normal to its orientation direction. Okay. So, also E is changing with time, right. So, here we see that the this we are talking about the first equation where the E is changing with time, and then H will be general and also change with the time. So, as the value of E will change with time, because this component is showing about the time varying field. So, when we have the time varying E field, so corresponding that value of H will be also changed. The same thing will happen in this equation, equation number 2, where the H is changing with the time. So, when the H is changing with the time, so correspondingly E will also change. So, we can say the transportation of energy or the wave propagation will specifically depend on these two equations, where the time varying fields are occurring, and in the first equation E is changing with time. So, correspondingly H value will change, and in the second equation H value is change with time, correspondingly E value will also be changed. Okay. So, this is the comprised summarized way of these equations, how the electric or magnetic field will change. Okay. Then now come to this point. So, velocity with which this effect moves away from the original point is the velocity of light. So, these are some introductory part which we are talking about right now. So, in this the uniform plane wave. Okay. So, in that uniform plane wave, what is the definition for that? In which the both the fields E and H lie in the transverse plane, right. So, in short we can say that when we have this type of any field, so in this the electric field and the magnetic field, suppose this one is the electric field and this one is the magnetic field. So, these two components will lie on a one plane, right, and correspondingly the wave propagation will be in this direction. Okay. If this one is x direction, this one is a y direction, then it will be the z direction of the wave propagation. So, this can be the positive z direction or the negative z direction. So, uniform plane wave is when we have the electric and magnetic field E and H component which lie on the transverse plane, and this plane whose normal is the direction of propagation. Okay. So, this uniform plane wave is characterized by the electric field and the magnetic field that have the uniform property at all the points across the infinite plane. And second thing is the plane wave has no electric or magnetic field component along its direction of the propagation. Okay. So, by this diagram also we can see that E and H component will be transverse in nature and it will be on the plane, and there is no component of electric and the magnetic field in the direction of z. So, in short we can say that Ez component or Hz component will be 0. So, these components will not be there because this and also we can say that Hx and the Ey, this will also be 0. So, these components will not be present because these components are these components in the direction of z is not there. Okay. So, okay, so in this case this is correct. So, this can be changed. So, this cannot be 0, but this can be changed, right. I am sorry for that. So, this portion is correct, that Ez and Hz will not be there, but Hx or Ey can be there, right. It can be there. Okay. So, now let us start from the lossy case. So, this lossy case is a generalized case in the EM waves, right. So, as we have discussed in the previous slide, that is a free space case, but now we will start from the lossy case, in the lossy dielectric case. So, in that lossy dielectric case, it is a medium in which the EM wave as the propagates losses power owing to imperfect dielectric. So, this lossy case is not a perfect dielectric or it is not a perfect conductor case. So, this is in between. Okay. So, it means when we have this type of medium, so losses of the power will occur regularly. So, in other words, the lossy dielectric, partially conducting medium or the perfect imperfect dielectric or imperfect conductor with the sigma is not is equal to 0 at that case. Okay. So, distinct from the perfect dielectric in which sigma is 0. So, it means the lossy dielectric case sigma is not 0. So, the Maxwell equation which we are going to use for lossy case, that is del cross H subscript S is equal to sigma plus j omega epsilon E s. So, what we are doing? We are simply if we come to this equation, what we are doing? We are using this equation, this one and this one. So, in this case what we are taking? We are taking the j is equal to sigma E and we are taking this d is equal to epsilon E. Second thing what we are doing? We are just putting that del upon del t, that is equal to j omega. Okay. So, this transformations we are performing here. So, in this equation we see when we do all these things, then del cross Hs will be equal to S as subscript for the lossy case, sigma plus j omega epsilon into Es. So, similar to the del cross Es will be minus j omega mu upon Hs, j omega mu into Hs, and del dot Es is equal to 0 and the del dot H is equal to 0. So, here the time factor e to j omega t has been suppressed in the above expression. So, what is the meaning of that? So, in this means shows that when we are using the del upon del t, that is j omega. Okay. So, at this point you have to take care about that. Okay. So, what we need to do? So, we want to find the wave equation in terms of H or the wave equation in terms of E. Okay. So, for those we have to use these equations. These two equations, we will start from this equation and we will put the values from here. So, here what we are taking? We are taking the del cross Es from here. We are taking this equation. So, this is the equation number 1. This is equation number 2. This is equation number 3. This is equation number 4. So, we are taking equation number 2. So, in that j omega Hs, so what we are taking the curl of these two equations. Every time you have to do the same procedure, you have to take the curl of that equation, okay, because we want the wave equation in terms of E. So, that is why we are taking the del cross E. Suppose we want to find the wave equation in terms of H, then in that case we have to take the equation number 1 and we have to take the curl both sides of this equation. So, right now we want the wave equation in terms of E. So, in this case we will take the curl of this equation. So, in both sides, so the equation will become del cross Es and j omega mu, and here what we will do? We will use the del cross H here. Okay. So, we are taking the curl of this. Next step is what? So, just use the identity of this, the del cross Es. So, this identity is like this one. this will the gradient of divergence of Es minus Laplacian of the Es is equal to minus j omega mu, and in place of del cross H we can use this equation sigma plus j omega epsilon into As. So, we can put it here. So, after that when you are using this, then del dot E S is 0, right. So, here we see the del dot Es is equal to 0. So, we can put del dot Es is equal to 0. So, this equation will come like this. Okay. So, this equation is similar to this one, and here what we have signifies that gamma square. So, gamma square we have signifies like this. So, this gamma square is nothing but the wave propagation constant. So, where gamma square is this, and here gamma is nothing but this is the propagation constant. Gamma square is equal to j omega mu in bracket sigma plus j omega epsilon. So, this is very important expression for the gamma. Okay. So, similarly we can express the magnetic field. So, what this is the analogy of this electric and magnetic field. So, the difference is what? So, here we have started the equation from del cross E is equal to j omega Hs. So, this is the case when we want to find the wave equation in terms of electric field. Suppose we want to find the wave equation in terms of magnetic field. So, what we will do? We will use the equation number 1 and we will take the curl both sides of the equation number 1. Okay. So, again we will get the del cross Es from here, and then we will put the value from del cross Es from the equation number 2 to the equation number 1. Okay. So, when we put it like this, then expression which we are getting, that is del square EHS is equal to minus gamma square Hs. So, this equation is representing the wave equation in terms of the H. Okay. So, you can see that these two equations are similar in nature, but the content which is changed, that is the E and H. So, this E and H are responsible for the wave propagation. Okay. So, in Cartesian coordinates, for example, each of these two vectors equation are equivalent to the 3 scalar waves equations, and one for each component of Es or Hs along the Ax, Ay and Az. Okay. So, in this way we can find the wave equations in terms of E or the in terms of the H. So, this signifies that about the electric field. So, this electric field is if we have the electric field in the x direction and the magnetic field we can also specify in the y direction. In this case we can say the wave is propagating in the z direction. So, here we see that del square x square and exx. So, it shows that this is the ex component in the x direction, this ex component in the y direction, this ex component in the z direction. So, this is the x component of the electric field. So, similarly, we can define in the y direction and we can also define in the z direction of the electric field. So, correspondingly, the x component of the magnetic field we can specify by this equation where the which is the change parameter is only h in place of E. So, similarly, we can define it like del square x square h s y and so on, and next is del square x del x square h s z. Okay. So, these are representing in the z direction, sorry, in the h component in the all the x y z direction, and this is representing the E component in the all the different coordinate systems of the Cartesian coordinate. So, this component fields of any time harmonic EM wave must individually satisfy these partial differential equations. So, these equations are very much important to find the wave equation in the different parameters. So, here we can specify all these things all together, then the solution of the equation which we will get it, that is Es, that is equal to Esz, and this z is representing the wave propagation in the z direction. So, here it is representing the x in the x component, right. So, two things are very important here. First is the direction of the wave propagation, which I said we are assuming in the plus z direction. Okay. So, wave is propagating in the z direction. So, correspondingly the x component of the electric field will be in this way. Okay, then we can substitute this into the equation which we had just derived. Here you can see, so in this equation we can put the value of E. So when we put it, then we will get the del square minus gamma square Exs z. So this subscript x is representing the x component of the electric field, S is a lossy case, here z is representing the direction of the wave propagation, and this gamma square, so this gamma is nothing but the phase, sorry, the wave propagation component or constants. Okay, so when we solve this equation, then in this case, because wave is propagating the z direction, so obviously the component of E and x will be 0. So this del square upon del x2 and del square upon del y2 will be 0. So the equation which we get after this substitution of these values, that is in this way, that this term and this will equal to 0. So this term will be left. So because when we solve this equation, so we have to convert this partial differentiation into the total differentiation part. So in place of small del square, we can put the d square upon dz square. So this equation nothing but the scalar wave equation, and when we solve this equation, then what we need to do, simply the solution in our BTech first year you have gone through that the solution for this one is just simply put d upon dz is equal to capital D and so on. So the solution of this equation, which we will get it in two terms, that is Exs E naught plus e to the power minus gamma z and E naught e to the power gamma z. So here when you solve this, the two eigenvalues which we will get, or the roots of this equation which we will get it, the plus minus of gamma. So this plus minus gamma is the roots of this equation, and based on that we can define the wave equation. So this wave equation is representing the two components, e to the power minus gamma z and e to the power gamma z. So here these components are representing as the wave propagation in the positive and the negative z direction. Okay. So in the first term we can see that this e to the power minus gamma z, this is representing the wave propagation in the positive z direction, and this equation e to the power gamma z is representing the wave propagation in the minus z direction. So it depends as per our application. So at what direction we want to find the wave propagation. Suppose the wave is contain these two components. So in this case, wave is propagating plus z direction, and after reflection it is coming to the negative z direction. So the superimposition of the wave propagation will occur and the standing waves will be generated. So I hope this concept is clear to all of you about the lossy dielectric case. So in the next lecture as well, we will discuss about much more about this application of the lossy case and the some more intuition about the wave propagation. Thank you very much.